Okay. Before we begin with the next lecture, let me once again request you to kindly switch off or put in silent mode your cell phone. Okay.
Good morning to all of you. First of all, I would like to thank Professors Parameswaran and Vishwanath for inviting me for this talk. And I'm very happy to be here among our own group of people, mathematics teachers. So today we are going to explore one of the topics which comes in applications of calculus, particularly differential calculus, of how to sketch a curve of a function using calculus. This is not any unknown topic, all of us know, but for some reason our students do not come prepared with these kind of skills, which is very much needed in understanding in many problems. When you see a function, you need to understand their behavior. What is happening as something happens, as x gets closer to something, or as x goes too far away, what is happening, all these behaviors, and where it has a maximum, where it has a minimum, all these things are a day-to-day activity for any mathematician. But with my own experience, I found many good students, even with outstanding on this thing, somehow they don't have that skill, probably they never heard of it. All it is if they are given y equal to f of x, then if you ask them to sketch the curve or graph of that function, all of a sudden immediately what they do is, what do they do? They plot points and then join. And that's all they do. And then you ask a question, okay, you plotted maybe 50 points, you join that, how do you know that it is in between, it is not wobbling or doing this and that? Then they don't have any answers for that. So it's, for some reason, maybe due to examination pressure or something, or it is not in the expected questions, it is not being focused. So that's what we'll explore today. So, curve tracing using calculus. A function can be given in more than one form. It may be, a function could be given in what are the forms we can give a function, define a function? By a formula, right? We could give a function in terms of a formula. What other possibility? I'm sorry? Relations. No, that's basically formula. Second thing, maybe we can give a function as a graph, right? That's one way of representing as a graph. What other possibility? Maybe if we have a set of data, we can give us a table of numerical values. Table of values. Maybe the other possibility could be one could define in an abstract way in terms of words, which may not be representable in any way. So, 4 in abstract definition. These are the 4 ways. Verbal statement, which we may not be able to transfer in terms of formula or graph or those kind of things. So that's what I mean abstract definition. Or maybe, I think as you said, maybe verbal statement. out of which we know given by formula. In fact, even this function concept evolved over many times. During Euler and D'Alembert time, there was a very heated discussion what it means to be a function. Because in those days, a function means it should be given by a formula. For example, something like this was not a function, x equal to 1 if x belongs to rational numbers, 0 if x is r minus q. This is set of all real numbers, this is rational numbers. For example, if it is given in segments, that was called as a graph rather than a function. So these things came into the discussion of wave equation, solving the wave equation, D'Alembert solution, and then heat conduction equation and all those kind of things. So it was Dirichlet in 1829, I think, who gave the precise definition of function which we use it today. So the formula thing may be given in terms of like this or anything else. As a graph, for example, out of all these things, so if we consider a graph, something like that. So we call this, maybe this is our y-axis, x-axis, this is our function y equal to f of x. As I always said, one picture is worth more than 1,000 words. Whatever may be the ways it is given, whether it is formula, table or this, if it is given in this form, we understand at least the behavior of the function, what is happening, what is, how tall somebody is, how low somebody is, what's happening at each point. For example, here, something special is happening at this point. Let's call x1. What is happening? It is at this point, there is a neighborhood in which the function value is, there is a neighborhood at which the function value is less than or equal to all other values in that neighborhood. So what shall we call that as? Local minimum. So here f of x1 is the local minimum. That's an important point for any function. So that's one thing. Second, this is also important for a graph. Why is it important? X-intercept, it crosses where it is 0. So this could be helpful in if we are solving an equation f of x equal to 0. So this is an important point. Let's x2. And this is also an important point. So this is at the origin, that is y-intercept. Then something happening here, let's call this as x3, at which something is happening, right? And similarly here, x4, x5, and x4, x6, and here it seems to be going let's call this as x7. Let's see, as x goes to, suppose assuming that this graph is like this, then f of x goes to something as x goes to negative infinity, right? Assuming that it is getting closer and closer to this, so this goes to that. So that's the long-term behavior we understand by a graph. Then we have a local maximum. Here we have a local maximum, local minimum. Here also local minimum. At this point something is happening. It is local maximum, all right, isn't it? We could find a neighborhood in which the function value is more than any other value in the neighborhood. So that point At this point we have that, but this is also local maximum, but this is also local maximum. There is a difference. What is it? Not differentiable. So at this point, this x5, at that point f is not differentiable. And then we have a local minimum here, and as x approaches to x7, f of x seemingly going to, so limit x approaches to x7 from left hand side, f of x from the graph, it's going to plus infinity. So if a function is given in the graph form, we are able to extract important informations about the function, and hence we understand the almost full nature of the function, isn't it? All right. Now, what is this called? I think generally this is called this vertical asymptote, right? Vertical asymptote. X equal to x7 is vertical asymptote. Yes? This is vertical asymptote. Horizontal asymptote is this, x-axis. Horizontal asymptote, x-axis, are same as y equal to 0. Besides this could also, some functions could also have a asymptote which are slanted lines, or maybe it is approaching a curve. So all these things are possible, right? Okay, now, so for a given function, it will be very important for us to get the graph of the function so that we can understand fully what the function is doing, what its behavior and everything. So our goal is to do, so okay, if it is given in graph, then we are at happy campers, so we can do all those things. But most of the time, the situations we deal with, the function is given by the formula. In which case, how do we find all these things? Because if we are going to get the graph of a function given by a formula, we have to understand what are the turning points in which it has local maxima or minima, or what are the points at which it is not differentiable, what are the points, what is the long-term behavior on both ways, x going to plus infinity, minus infinity, all those things. So this is where our calculus is going to be helpful. Calculus is going to be helpful. Now, before I erase this off, so let's look at the tangents here. What is happening to the tangent? Slope is decreasing and then starts rising, right? Coming to 0, and then it is increasing. So on this interval, look at this as x goes from left to right, our function values are decreasing. And here in this interval, up to this, the function values are increasing. So your tangent is always positive. But here your tangent, slope of the tangent is negative, slope of the tangent is positive. So slope means, how do we find the slope of a curve? Derivative. So that is essential. Second thing, then we have to look at how this tangent is changing, at what rate. That means to find the slope, we have to find the derivative. To find at what rate is it changing, we have to go to second derivative. So that will help us. Second thing also, see, even though this is, see, it is decreasing here and then increasing there, but it is looking differently. It's open up, right? Open up, and this is open down. So all these things are concave up and concave down situations. So now let us see First, let us look at just important statement of a theorem. A theorem which says that if f is a continuous function on an interval, right? If f is a continuous function on an interval, if you have a and b 2 points in the interval at which f of a is less than f of b, for example, and if you take any value in between f of a and f of b, then let I be an interval and a comma b belongs to I, let f be a function from I to R be continuous. If k is such that f of a less than k less than f of b, then so f is a continuous function, f of a is less than f of b, and this value k is in between, then what can we conclude? So look at this, it's a continuous function, f of a is here, f of b is here. It's a continuous function on the whole thing. So what should happen? And k is a value in between this. Then, anybody who remembers? Yes? No. Exactly. So there exists an x between a comma b such that f of x, maybe let me call x0, equal to k. This is called as exactly, thank you, intermediate value theorem. This is due to Bolzano. This helps us to identify if f is positive at one point, negative at one point, it has to have a 0 in between. That helps a lot in identifying many things. So let us see. Theorem 1, Theorem 2. Let f from I to a R be a continuous function. If f of c, if c belongs to I and f of c is a relative which is same as local extremum, that means it is maybe local minimum or local maximum, then let's look at our picture. If it is so at this point we have a local minimum, at this point we have a local maximum, local minimum, local maximum, and all those things. Then what should happen? then see, look at this, at the maximums and minimums, it seems to be the tangent is horizontal, right? Tangent is horizontal. Tangent is horizontal here also, is it? There the tangent doesn't exist, the derivative doesn't exist. So that is, let's leave out that. So if f is differentiable at the point C, either the derivative should be 0 or it doesn't exist. So then one, either, or maybe, then either f dash of C equal to 0 or f dash of C does not exist. These points are important for us, does not exist. These points are important for us to find where we may have local maximums and local minimum, right? And these points are called any such C, this is not part of the theorem, any such C is called a critical point. This theorem is due to Fermat. Which helps us locating where local max, local min could happen. If we look at local minimum, look at one side, as we have seen, the slope is negative on one side at the local minimum. To the left of x1, to the right, the slope is positive, and the slope is 0 if it exists there. So the function is decreasing to the left and increasing there, so then we will have a local minimum. Similarly, to the point to the left, the function is increasing and then decreasing, then we will have a maximum. So it is important for us to find where a function is increasing, where it is decreasing. So I'm going to be a little bit sketchy on the statements, in the sense that we'll do at least one or two examples. So I'm going to be just stating what they are. If f is a function from I to R is differentiable, then, or maybe let f be differentiable one, if f dash of x is greater than or equal to 0, that means the slope is positive on the interval I, then f of x is increasing on I. If f of x is less than or equal to 0 on I, then f is decreasing on I. Then once we know this, then we know if it is decreasing and then increasing at a point, then we have a local minimum, and then similarly local maximum. So that's what, using this we form a test. Using first derivative we form a test which says, called first derivative test. What does it mean? At a point, you take a critical point. To the left, if it is increasing or the positive slope, to the right it is negative slope, then it has a relative maximum, similarly with minimum. So that's our first derivative test. So I'm not going to write all those things. But the derivative 0 at a point does not mean it has to have a maximum or minimum. For example, f of x equal to, for example, x cube, where x is in R. We know the graph of x cube looks like the derivative is at 0, but it doesn't have a maximum or minimum, and that is obvious because f prime of x equal to 3x square, and it is 0 only at this point. If you check the sign of f prime, it is positive here, plug any point, so it is positive here, it's positive here, so the sign doesn't change, so f of 0 is not a local extrema. See this increasing, now the question is, given a function we can locate where it has a local extremums, and we can find out the intervals where it is increasing, where it is decreasing, right? Will that be good? Will it not be good enough for us to get a graph? Is it not? Because that's what it is important, where it is increasing, where it is decreasing, what maximum is, what minimum is. Will it not be good enough? Suppose, for example, so this is A to B. Suppose that we know that f of x is increasing on AB, increasing on AB. Will it describe our function in an accurate way? Suppose I know the value here, will I be able to, or will we be able to get the graph, at least sketch correct? We know that it is increasing, right? Can we? See, the increasing could be, this is increasing, right? This could also be increasing. Maybe let me not do the same thing. So there are two possible ways of increasing. But this behavior is different, that behavior is different. So we have to find out which behavior it is having on each interval or wherever it is changing, right? So that is for this what? So here the rate at which your slope is changing, the slope is increasing. Here it is decreasing. So this is what the concept of concavity is very important in identifying whether it is going up, going concave down or concave up. So let us have that theorem 4. Let I be an interval if f double dash of x is greater than or equal to 0 on, on I, then f of x is concave. So f dash of x is positive means, f double dash of x positive means f dash of x is increasing. So this is concave up. If f double dash of x is less than or equal to 0 on I, this is on I, then f of x is concave down on I. So we have seen that if we assume that f double dash is continuous, it's positive at maybe on to the right of it. F double dash is positive on this side. F double dash is negative on this side. That means f double dash must be 0 at that point? Is it not? Suppose if you have a point, for example here, this is f double dash is negative. Here f double dash is positive. It is 0 there, right? So the point at which, maybe let me say this, if C is such that f double dash changes sign at C, then this point C, f of C on the graph is called the inflection point. Inflection point. But double derivative 0 again does not mean it has to be an inflection point. Sure? Exactly, good. F of x equal to x power 4 will look like very flat at the origin and have this. If you take the double derivative, then you'll see that there is 0 at the origin, but it does not change the sign. F double dash does not change the sign. One more thing, then we'll do a problem. Second derivative test. What does second derivative test say? Well, of course, it involves second derivative of the function, right? So let's see. Let f be defined on I to R be differentiable up to order 2. Up to order 2. Suppose that f dash of C equal to 0 for some C in I. That means C is a critical point. That means potentially at C we may have a maximum, relative maximum, or relative minimum, or neither, right? Suppose that if f double dash of C is positive, then f of C, very good, f of C is a relative minimum or local minimum. 2, if f double dash of C is negative, then f of C is a relative maximum. 3, if f double dash of C equal to 0, the test fails. Test is inconclusive. But the first derivative test will always work. Second derivative test is easy if we can calculate all these things, but it may give us a problem if it fails. Now let us do a couple of problems. Let me take up a let's consider f of x equal to x power 4 minus 8 x cube plus 5. I think this should be 3. 12, 24, yes. Now we are going to work this problem, just doing step by step what all the things to do. So this function is differentiable as a polynomial function. Now let's find f dash of x. First step, finding critical points. F dash of x is 12 x cube minus 24 x square, that is 12 x square x minus 2. Is that right? So that implies x equal to 0, x equal to 2 are critical points. What are we going to do with these points? Well, if our problem is just to find the local max, local min in quick, then maybe we could go for the second derivative and evaluate and find out. But also when we want to get the graph of this function, we need to understand whether it is increasing, decreasing, concave up, concave down. So let us do the testing of increasing, decreasing. So this is 0 and 2 sine of f dash of x, that's equal to 12 sine of f dash of x, that's nothing but what, 12 x square x minus 2. So here is where our f dash is a continuous function, right? So if it is 0 at those points, then on the rest of the intervals, either it must be either positive all the time or negative all the time. That's our intermediate value theorem helpful here. So let us choose a point below this, say for example negative 1. Negative 1 square is positive, negative 1, this is negative, so this is negative. No, it may not work all the time like that.
Why increase of the form x power a, x minus a power n1 and x minus b power n2 and so on? These are even powers.
When you have a particular problem, it would work. Yes. This is in the even degree, right?
No.
This one. Yeah.
That,
right. Then it will have, yes, okay. So here what is happening? Where is positive? X square, say for example 1, this is positive, 1 negative, so this is negative. Is it not? And more than 2, this is positive, so that's positive. So that means f of x is going to be decreasing here and decreasing again here, and f is increasing. Is that right? Please check my work. I'm very easy to make mistakes. I always make mistakes. So check my work. Now this implies what? This implies f is decreasing on minus infinity to 0, union 0 to 2, and we can even say the full thing, and increasing here you can include, nothing wrong with that, but generally see, but you can include, see, if you are saying for example, suppose if this is the interval, you are saying that 0, it is decreasing on that, nothing wrong with that. But decreasing or non-increasing or mutually exclusive. Non-increasing.
And sometimes it is put as a closed loop.
Yeah. No. Yes.
People wanted to know whether you have to use a dash that's strictly greater than 0 for strictly increasing. That is a serious doubt everybody has.
If you are saying, okay, so here I am using decreasing in the sense of x1 less than x2 implies f of x1 greater than or equal to f of x2. If you are talking about strictly increasing, that you have to go with the textbook you are using, whatever they are following, follow that notation. If it is, this is what I am calling as a decreasing. Anytime x1 less than or equal to x less than x2 implies this. Oh, for increasing you mean? Not necessarily. For example, x cube. The derivative is the derivative f of if you take f of x equal to x cube.
Suppose decreasing on the interval minus infinity to close at 0. Union 0 to 2 close to.
That's okay. Yes. On that interval, if you are talking, see, you are increasing, decreasing. You are talking on an interval. You can include that. My only concern is you should not take my word. The textbook, whatever it says, follow that because the students are going to take your exams according to that notation. Yes. No, that's what I'm saying. See, the understanding, as long as you understand the increasing, decreasing definition in this way, you can include, nothing wrong with that. But when you are teaching the students, when they are writing their answers in a particular way, if you are changing the book may be using one notation, if you are teaching the other way, then they will be in trouble. So you follow that notation, but in understanding, you can say that it is decreasing on this, and I'm sorry. I'm sorry. Yeah, I'm here. So I will have to write something on this, right? I haven't done that yet. Oh, in the meantime, there were questions, so I'm trying to. So it is increasing on 2 to infinity.
Now the question is, suppose we are including 2 there, can we include here also 2 to infinity?
Yeah, you can say that because it satisfies that definition. Anytime 2 and this thing, f of x1 greater than f of x1 less than or equal to f of x2, it would satisfy. You can, yes. You can include, so instead of this, you can include this to 2, nothing wrong with that. I'm going by the, whatever we found, I just record, and then, yeah, we can include that, nothing wrong with that. Okay, questions? So, increasing on this, I know this endpoint problem is a big problem because this is a border issue, right? Yes. Yes.
Whenever I'm going to use the concept increasing but not strictly increasing, use closed interval.
Right. Yes, sir.
Function is increasing.
Yes, sir.
Perfect square is always non-negative or 18.
Non-negative.
X square minus 4x plus 4 is coming, f dash of x. We say it is increasing, not strictly increasing. Since x minus 2 whole square, the x minus 2 whole square is always non-negative. We are telling it is increasing.
Increasing, right? Yes, sir. Yes, sir. Sure. See, this is about discussion. Yes.
We are going to take it as a first interval. We talk about the
Yes.
it should be existing left hand side derivative as well as a right hand side derivative. In the case of a closed interval, if you talk on the lower side, you cannot talk about the left limit. If you are talking about on the higher side, you cannot talk about the right limit.
Right.
That's why always if we exclude that particular point, we write it in the open interval. That is the meaning for it.
No, I agree. But when we have a function defined on the closed interval, our derivative,
It is a closed interval.
right,
It is going to be, I cannot talk about the left derivative for a particular point which is on the lower end. On the higher end, I cannot talk about the right hand side.
true, only the
Therefore,
one-sided limit.
it should be in the open interval so that I can talk about differentiability at a particular point. Then I can apply all your ideas. Therefore, it should be in the open interval, not in the closed interval.
I agree. And his point is that when we talk about differentiability, we have to talk about differentiability at a point. So we have to talk about left limit, right limit. But when we have also the convention, when we are dealing with a closed interval, when we are talking about the derivative on the closed interval, means we are talking only one-sided limits on both endpoints. So that's what I was saying. So what my suggestion would be, you follow the convention for the student's sake of the book. But in understanding wise, it's not going to make a difference. Okay. All right. Now let's check for the second derivative. F double dash of x f double dash of x 12 times 2x times x minus 2 plus x square. Now, so that tells us that, is that right? We can factor x out, 12x, 2x minus 4 plus x. So this is equal to 12x, this is 3x minus 4. So f double dash of x equal to 0 gives us x equal to 0, x equal to 4/3. These are points, the points where the second derivative is 0. Some books call these points as hypercritical points, but that may be very few. Some books call these points as hypercritical points. But then, now let's check the concavity. So x equal to 0, this is 4/3, sine of f double prime. If we choose minus 1, for example, this is negative, so it's positive. And 1, that's negative. This is positive. So the behavior of f is from this we conclude this function is like a cup, here it is like a cap, here it's like a cup, right? So this implies f of 0 comma f of 0 is and 4/3 comma f of 4/3 is a points of inflection or inflection points. Oh, by the way, we didn't calculate after this we could calculate local max, local minimum, right? So let's calculate that. So at 0, f of 0 was, I erased my function, f of 0 is 5, right? So that's right. And f of 0 is, that's not a local maximum or minimum, so we leave out. So f of 2 is, what is f of 2, please? f of 0 is 5, right? But that's not, at least we know the value, but what is this? Minus 11. So now let us, do we have all the information needed for getting the graph? Let's also look for behavior of this function as x getting large on both sides. So our function was f of x equal to 3x power 4 minus x cube plus 5. We want to know limit x going to infinity of f of x. X power 4 minus 8x cube plus 5. How do we deal with this? See, this is going to infinity, right? 3x power 4. This is also going to infinity, and this is plus 5 we can ignore. So then we have infinity minus infinity, so we are not able to decide. How do we deal with this? No, L'Hopital rule doesn't say for these. Maybe this is, I don't know. So now let's see. Let's factor out what we could do, right? So here is, maybe we could write this as this way. I'm going to factor out the leading power. X power 4, let's take that out. Then we have 3 minus 8 by x plus 5 by x power 4. These are one and the same, because we are worried about x going to infinity, so x is not going to be 0. We are far away from the 0, so we are okay now. Now, as x gets really large, 8 over x is, this is also 0. See, in this form we are not able to decide what is happening, but in this form we are able to do that. And this is going to infinity. So the whole thing within the square bracket goes to 3, and this goes to infinity, so this goes to plus infinity. Similarly, you can argue for the other side. That means our graph is going to shoot up on both sides to infinity. Now let us graph this. So anyway, so let's use all these data, see if we can get a reasonable graph. Now, since I have erased all of it, you have to help me. Now, what are the important points? 0 was 1 point, 2 was another point, 4 by 3 is also, so this is 1, maybe let me make it 2 here, this is 1, so 1 by 3, this is 4 by 3. Any other important point? Anything else? So now, so we know that it is decreasing here, and concave up, concave down where? I erased that. So I think 0, 4 by 3, this was concave, up, down, up. Okay. Yes? Sure.
Since the function is decreasing from minus infinity to 2, the point of inflection cannot be at 0.
Yes. No, wait. No, this is not for the point of inflection. This is for the increasing, decreasing. Point of inflection should be where the concavity changes.
That does not change the sign. It won't change at 0.
No. See, this analysis is for increasing, decreasing of the nature. Nothing to do with the concavity of the function. Concavity we want to talk about with a second derivative. So,
It is good only for inflection, no? If that
yeah.
doesn't change the sign.
Yeah. What doesn't change the sign? What doesn't change the sign?
No. Even though it is for increasing, decreasing analysis,
Yeah.
still if that doesn't change the sign around 0.
Right.
It is still confirming the
No, I think madam's point was that this is negative on this side, so it cannot be inflection point. So what I'm saying is, this we cannot use it for that purpose. Inflection point is a point where your second derivative changes sign. Second derivative changes sign. So that's the analysis, right? Okay, now let's label all these points. So at 0 it was 5, right? So this is 1 point. And then what are the points? At 2 it was minus 11. So this is 5, negative 5. This is 10. So negative 11 is this. Okay. At 4/3, please calculate. At 4/3, it's a fractional calculation, but I'm sure we can do that. So, and few more points. Maybe if you have a calculator or something, let's calculate at negative 1 and negative 2, maybe at 1 and maybe at 3. Let's calculate the points at these things. This is 2 comma negative 11. F of minus 1 is 16, so it is way up there. 16, so it will be coming down like this. It is concave up there, so it is going to be looking like that. Right? It should be concave up, so it should be looking up at this point. Negative 1, you said 16, so it's way up there, so it's coming down like this. Then it is concave down on this interval from here to that. So what is at 4/3? I'm sorry, that happens to be a fraction. Minus 120. So that is, maybe I should change my scale. Minus 4 point something. Wait. Let me change my scale. No need. Okay. 5, this is 11. Minus 4 point. Okay. At that point, right? 1 is, at 1 is 0. At 1 it is 0? Yeah. Right. So here it is going to be concave down, so it is going to be like this. The concavity changes at that point. At this point also, it is like that. At 2 was 11, right? Minus 11. So now this is concave down. Then it is going to be concave up here, right? So it's going to be at 3. Huh? 32. 3. Well, 3 is what? 981 times 3. 32. 3 is at 32, way up there. So definitely it goes down, up like this. Okay. Oh, I have made some problem sheet. I will give it to professors. They can copy and give it to you so that you can do some exercise on that. And another thing is, Questions? Another thing also, maybe we could teach students when they are free time, if we know the graph of f of x, how do we get the graph of f of x plus h? Shifting, right? This also they don't have a very clear idea. Shifting horizontally or shifting vertically by adding a constant, c times, constant times what happens, these kind of things. And another thing is my request, which you may be already doing it. Generally when we teach the students, it is one way to do that, well, give one step, step 1, step 2, step 3. The students do that monotonically without knowing why they are doing it. And maybe if we make them some time and saying, what is the importance of this step? Why are we doing it? If we do that, maybe they will have the understanding why they have to study instead of rather than just for examination purposes. And I'm sure that CBSE schools are following that, but state board, my niece is going through +2 now, but when I go home, I talk with her sometime. When I ask questions, she's able to do the problems, but she simply says, this is what my teacher told me, and why we have to do and all those things. Maybe at that young age, if we teach them the curiosity and what we have to do and why we have to do, what is the purpose of that, that will probably light fire in them, which will help a lot. Yes?
See, even without algebraically calculating, f of 2 is -11 and f of 3 is 32. So when we say graphically,
I'm sorry, you are right.
the x-axis between 2 and
Exactly. I'm sorry, this is my mistake. This is negative, very good point. This is positive, so there should be a 0 in between. Intermediate value theorem, right? I'm sorry. Thank you very much. Thank you. So it should be probably going steep. So I wanted to have the concavity, so I zoomed in that way. Thank you very much. Thank you. And so another thing is that our job, which you all will agree, our profession is much more important. I'm not putting down the medicine profession, but I'm saying that medicine is very much needed for everyone as long as we live and the world lives. But even more important is our job, and which you all, I'm sure, agree. So let us try to do our best, what we can do to enlighten mathematics in them so that they can use and apply wherever they go, whether it is engineering or science or anything. So I thank one and all for listening to me. I thank the organizers for giving me this opportunity to talk with you this afternoon. Thank you very much.